Okay. Thank you very much, Matthias. Okay, let me see if I can share screen. I should be able to do that. Okay, can you see it? Cool. Okay, so first of all, thank you very much to the organizers, Martin, Eduardo, Red, for the invitation. It is a pleasure to be here. Okay, let me start with the notion of a random graph. Please interrupt me should you have any questions. So there are many different probabilities that we can put to the space of all the finite graph, but perhaps the most well-known model is the Erdős-Rényi model. So what they do, they fix a particular probability P, okay, so a real number between 0 and 1, and they get, so for a bunch of vertices, say n vertices, they are going to decide for each pair of vertices, they will toss a coin, and they will decide whether they add this edge or not. Okay, they add the edge with probability P, and they do this independently for every pair of vertices. So at the end, they get this random graph. So this has many applications inside mathematics, outside mathematics as well, and there is a natural generalization to higher dimensional simplicial complex. So what do I mean by a random simplicial complex? Again, this depends on the probability, how you want to measure, okay, the probability of a given simplicial complex to appear. And some of the most well-known models, for instance, is the clique complex model, in which we again start with a set of vertices. We construct the Erdős-Rényi model exactly in this way for just one particular probability P. And how do we turn this into a higher dimensional simplicial complex? When we consider the clique completion. So recall, in the clique completion, the simplices are exactly the sets of vertices which are pairwise adjacent. Okay, so the cliques of the graph. So the clique completion of this graph here is this thing. So every time we have an empty triangle, this will be a full triangle in our simplicial complex. Okay, so okay, we turn this into a higher dimensional simplicial complex, but perhaps this is not natural in the sense that many simplicial complexes cannot appear in this setting. Okay, there are other models which I don't have the time to discuss now, but the model that I want to I do want to discuss is the multiparametric model. So this is a natural generalization of the clique complex model, and the idea is that we begin again with a bunch of vertices. These are the potential vertices of our complex. And instead of fixing just one probability, we are going to take one probability for each subset of the vertex set. Okay? And we are going to construct this complex skeleton by skeleton. So we begin with the vertices. We are going to decide for each potential vertex whether this will be a vertex in our complex with probability P sub sigma, where sigma is just this one point set of one vertex. So when we end this, some vertices will be not part of our complex, only some of them will remain. And then for each pair of vertices, we are going to add the corresponding edge with probability P sub sigma, where now sigma has cardinality 2. Okay, when we do this, we pass now to the two-dimensional skeleton. So for every empty triangle, we are going to add with probability P sub sigma, where sigma is now the 3-point set, the two-dimensional simplex, and we move on skeleton by skeleton. So this complex may or may not be clique, and it is easy to check that if all the probabilities are positive and less than 1, any simplicial complex in n vertices can appear in this way. Okay, and it is easy to check that for some particular choices of this P sigma, we are taking again this clique complex model. So this is a subcase, this very general model. So what is the general questions that we are interested in is how do these asymptotically homotopy properties of the complex appear? I mean, when the number of vertices tends to infinity, what can be said in general about homology groups, homotopy groups? Some group theoretical properties of the fundamental group have been studied, other geometric properties. Okay, so what can be said in general for a random simplicial complex? So if we want to say anything about this general multiparametric model, it is very hard to compute or even to estimate a probability of something to occur if we don't put any restrictions in this set of probabilities. That is why Farber and Costa introduced a subcase of the multiparametric model in which all the probabilities lie in a fixed interval AB. So here the number of vertices will increase, but this interval AB is fixed during all the time. Okay, so this contains in particular the case where all the probabilities are 1/2, for instance, okay, which already sounds very natural. So for this case, they managed to prove, for instance, the following result, that when the number of vertices tends to infinity, then the probability that the Betti numbers up to degree D are all trivial tends to 1. Okay, so I mean, in general, there will be no poles up to dimension D in the sense of rational homology. Okay, the Betti numbers, the rank of the homology. So this is already perhaps surprising. This is all in the context of the medial regime. Okay, everything I will mention is inside this notion of random complex. A different result that they prove is that the probability of the fundamental group being trivial also tends to 1 as the number of vertices tends to infinity. These two results are independent. Okay, this speaks about rational homology, and this is the fundamental group. Now, a generalization of this second result here is this one here, that proves that the probability of K being 2 connected tends to 1. So recall, 2 connected is connected with trivial fundamental group, but also trivial second homotopy group. That is, every continuous map from the 2-dimensional sphere into the complex is null homotopic. Okay, it's homotopic to a constant map. So this is much stronger. And how do they prove these things? I mean, it is very hard to compute the probability of a complex being simply connected if the word problem says that in fact there is no algorithm to check whether a particular finite complex is simply connected or not. Okay, there is not such algorithm, but the general idea, if you want to estimate the probability of a particular topological event to occur, is to define a combinatorial property whose probability to occur is much easier to be computed, and then prove that this combinatorial property implies the topological property that you are interested in. Okay, so in that case, you are only going to get a lower bound for this probability, but this is exactly what we want in these cases where you want to prove that some probability tends to 1. Okay, so what is this combinatorial property that Farber and co-authors define? Is the notion of an R-ample simplicial complex. Okay, so this is a combinatorial definition, which I will not recall today. We will not need this. And they prove that as long as they increase this degree of ampleness, they get better connectivity properties. Okay, they do this until dimension 2. And on the other hand, they prove this is the probability, the part of the combinatorics and probability result, that for any R, the probability of K being R ample tends to 1 as the number of vertices tends to infinity. So if you see, when you glue these two last results, we get this theorem here, because the probability of K being 18 ample tends to 1, and in particular the probability of being 2 connected tends to 1. Okay, so this is how this combinatorial notion, which I did recall, implies this result here. Okay, so the natural question is, what can be said in dimensions greater than or equal to 3? I mean, is there a degree of ampleness which implies 3 connectivity, 4 connectivity, and so on? Well, in order to answer that question, we introduce a new notion, a new combinatorial notion, which I will define now, is the notion of being R-conic. So a complex K, a simplicial complex, is R-conic if every subcomplex with R vertices or less is contained in a simplicial cone, equivalently in the star, the closed star of a vertex. So let me go to an example. I claim that this one-dimensional complex, so this is an empty square, is 3-conic. What do I have to prove? That any subcomplex with 3 vertices or less is contained in the star of a vertex. Recall that the star, for instance, of this vertex is this L here. Okay, the star of a vertex is the set of all the simplices which contain the vertex and their faces. So the star of B is just this L here. Well, but if we have a subcomplex with 3 vertices or less, it is contained in one of these L, in 2 consecutive sides of the square. So it is clear that it will be contained in the star of a vertex. A generalization of this, when we take the suspension of this square, is this octahedron. So this is a triangulation of the 2-dimensional sphere, and it is easy to check that this is 5-conic. In general, any simplex will be R-conic for any R. More generally, any cone is R-conic for any R. So this is the definition that we are going to work with today. And the new results that we prove are all this here. So first, okay, I didn't recall the definition of R ample, but from the definitions, it is trivial to check that R ampleness implies R conicity. So in particular, anything that would prove for R conic complexes will hold for R ample complexes. Then we have these 2 results here, which are the same as these 2, just that we improve this, changing ampleness by conicity. This third result here, it is an improvement of this third result in 2 different ways. I mean, we improve this 18 has been reduced to 8, and the ampleness has been changed by conicity. But what is more important, and regarding this red question here, we prove that given any D, there exists some degree of conicity, which implies deconnectivity. Okay, so this generalizes, without precision in these numbers, all these results here. So gluing this with the probability result, what we get is that given any D, the probability of a complex being deconnected tends to 1 as the number of vertices tends to infinity. So in general, there will be no holes in a dimension smaller than or equal to D. Okay, so this is stronger than the result that we mentioned in the beginning with Betty numbers, because here we are speaking about homotopy groups. Okay, it's something stronger than rational homology being trivial. Okay, so what I want to do in the rest of the talk is give you just some ideas of how to prove these results here. Okay, so let me first observe what do I have in the pen here. Something that is easy to check is this result here. Okay, that 2 conicity implies connectivity. So once again, we still have the definition here. 2 conicity means that any subcomplex with 2 vertices or less is contained in the star of a vertex. Why does this imply connectivity? Well, if we have 2 vertices of our simplicial complex, this is a subcomplex of cardinality 2 with 2 vertices. So this has to be contained in the star of some vertex. So it means that these 2 vertices are connected with a very short path. Okay, perhaps this complex is contained in the star of one of these 2 vertices. So in that case, there's still a shorter path, okay, of length just 1. So the vertices, they are really close one to the other, so the complex is connected. How do we prove that 4 conicity implies simple connectivity? Well, we have to prove that any loop, okay, so every element in the fundamental group is in fact trivial, can be contracted to a constant loop, okay? So this is the idea of simple connectivity. So what we are going to do, we take a representative, a discrete representative in the 1-dimensional skeleton of this given loop. So this is the notion of the edge path group. We can always take a sequence of edges in the 1-dimensional skeleton, which represents the given loop. This could have self-intersections, okay? And what I claim is that, well, the 2 conicity already implies that if I take this first vertex, this V0 and V3, as we have just seen when we studied 2 conicity, there will be a path joining V0 and V3, which is very short, okay, of length 2 or length 1. So we have managed to divide the original cycle into smaller cycles. So by induction, each of those will be trivial in phi 1, and therefore so will be the concatenation. Okay, so this is the idea of the proof. Perhaps it sounds a bit strange that we are only using 2 conicity, while the statement says 4 conicity. Is because in this induction step, we have in fact used that this number L is greater than or equal to 6. For the basic cases of the induction, we will need this 4 conicity. Of course, for length 4, we know that the square is 3 conic, and it is certainly not simply connected. So for the square, we will need 4 conicity. Okay, the others can be, okay, are easier to prove. Okay, so this is the idea of this second result here. How can we prove this, the following result? That 8 conicity implies 2 connectivity. For maps that begin in the start in the 2-dimensional sphere, perhaps there is not such a nice description as we have for the fundamental rule, but still we will be able to copy this idea. Okay, so let me introduce the following notion. So we'll say that if we have a simplicial complex M and we have a subcomplex D, which is a triangulation of some disk of any dimension, okay, and say that it has at most R vertices, then if we are able to replace this D by a cone over the boundary, the new complex that we obtain is said to have been obtained from the original complex by an R starring. This idea already appears here. I mean, these 3 edges, okay, this is a triangulation of a 1-dimensional disk in our complex M, which is this blue complex here. And we have replaced this disk by a cone over the boundary. So the boundary of this 1-dimensional disk is just the 2 extremes, B0 and B3, and the cone over the boundary is these 2 green edges. So we have replaced this disk by this one here, and we obtain a smaller, okay, a shorter path. So here we have an example of an R star ring with R equal to 4, okay, because the number of vertices of this disk is 4. So why is this notion important? Well, this is because of the following lemma, okay, which appears here. So let me go through the statement with the following picture. So the statement is the following. We have 2 complexes, M and K. K is assumed to be R conic, and there is a simplicial map phi from the complex M into K. Okay, and we assume that we can perform an R star ring in M. So that is, we change a subcomplex, which is a triangulation of a disk. In this case, this is a 2-dimensional disk, by a cone over the boundary. Okay, so the boundary of this disk looks like S1, okay, this circumference, and we take the cone. So this is a new triangulation of the disk. Okay, so we obtain this new complex, and the statement says, okay, we should prove that there is a new simplicial map from here to here, a homeomorphism between these 2 complexes, and the new simplicial map is essentially the original, in the sense that it is homotopic to the original composed with this homeomorphism. So in particular, any homotopy property that happens with this map here will also happen with that one. Okay, so one of the 2 will be homotopic to a constant map if and only if the other is homotopic to a constant map. So how can we prove this? Well, we already said that we replace this disk by a triangulation of the same disk. So it is clear that there is a homeomorphism here from one disk into the other, which is the identity in the boundary. So it extends with the identity to the complement of the disk. So this is the homeomorphism. How can we define this new simplicial map that goes from here to here? Well, we know that since the number of vertices in this disk is smaller than or equal to R, so this is the notion of R starring we just defined, then the image of D through phi will have at most R vertices, and since K is R conic, this subcomplex will be contained in the star of a vertex. So what we can do, we can keep the values of phi in all the vertices which are different from W, and W is now mapped to the new vertex B. Okay, so it is easy to check that this is a simplicial map, that every simplex is mapped into a simplex because of this property here. Okay, we only have to check what happens with the new simplices, I mean these triangles here in the picture, and because of this property, they will all be mapped to a simplex of K. So to finish the proof of the lemma, we have to check that there is a homotopy, that this triangle commutes up to homotopy. And in order to do that, it suffices to prove that these two maps, they are homotopic, but only in the disk. Okay, so in the cone over the boundary. If we prove that they are homotopic in the disk with a homotopy which is relative to the boundary, we are done, because then we extend this homotopy with the identity in the complement of the disk. And how do we prove that there is such a homotopy? Well, a homotopy is just a map from the cylinder of the disk into our complex K. Okay, and we know that in the bottom part of the cylinder, we want it to be this map. In the top part, I want it to be this map. In the boundary of the cylinder, I want to have it has to be constant. I mean, it's the same this map as this one here. So this partial map is already defined in a sphere. Okay, and since it takes values in this contractible subcomplex, it is null homotopic, so it can be extended to the interior of this disk. And this is why we have a whole homotopy between the two maps. Okay, so once again, what we did, the statement of the lemma, is that if we change this simplicial complex by a simpler one, in the sense that here we have reduced the number of vertices inside the disk by just one, okay, then we get a new simplicial map, which is homotopically essentially the same as the original map. What I care is one is null homotopic if and only if the other is null homotopic. Okay, and the last ingredient that we need is this version of the simplicial approximation theorem that essentially says that any continuous map can be approximated by a simplicial, a combinatorial map. So if we have a continuous map between two compact polyhedra, and we triangulate the domain with very small simplices, this should be made precise, but with very small simplices, then there is a simplicial map which is homotopic to the original continuous map. Okay, so up to homotopy and subdivision, every continuous map is simplicial. So what do we want to do? And this is the important proof today. So this is the important statement, is we want to prove that 8 conic complexes are two connected. Okay, so if I want you to take something home, is the idea of the following proof. Okay, it will be geometric. So what do we want to prove? That the complex is two connected. So we already know that this is simply connected. So we only have to check that every map from the two-dimensional sphere into our complex is null homotopic, is homotopic to a constant map. So this is what we want. And what do we know is that every subcomplex of 8 vertices or less is contained in the star of a vertex. So this is the hypothesis. So we are going to consider very particular triangulations of S2. So we are going to triangulate the square with some rectangles. Okay, here the number of rows and columns is the same, but it could and it should be different in general. So then we triangulate we subdivide each rectangle in two triangles, exactly as it is in this picture. We identify the left and the right margin of this square to obtain a triangulation of the cylinder. Then we take a cone over the top part, a cone over the lower part, to really have a triangulation of S2. Now, what I claim is that if the number of rows and columns here is big enough, I mean, if all these triangles are small enough, we can use this simplicial approximation theorem to find a simplicial approximation of F. Okay, so there is a simplicial map which is homotopic to F. So now we have reduced the proof to proving something more combinatorial, and it is that this simplicial map is null homotopic. Okay, so I forget about this F, I want to prove that this one is homotopic to a constant one. But why is this triangulation important? Because here we can identify a subcomplex, which is a triangulation of a disk, which has exactly 8 vertices. So by performing an 8 starring, we can replace these 2 inner vertices, we can replace this disk by a cone over the boundary. So this is a new triangulation of a 2-dimensional disk, and we have decreased the number of vertices by 1. So in that sense, this triangulation is simpler, and the lemma that we just proved says that there is a new simplicial map from here to here, which behaves exactly as phi. So one is null homotopic if and only if the other is null homotopic. But now, in this complex, again, we identify a disk with 8 vertices, so we can perform a new R-starring to obtain a new triangulation, which comes together with a map from here to K. And again, we repeat this process at the end. So recall that the left and right margin, they are identified. So this is still a disk. And we get this complex here with a simplicial map from here into K, okay? Which is null homotopic if and only if the original is. But what is important about this triangulation here? Well, it looks exactly as the original one, only that the number of rows has been decreased by 1. So by an inductive argument, we are going to be able to eliminate all the rows here until we obtain something very flat. Okay, it could be like very long, but flat. And by performing more 8 starrings, in fact 6 starrings are enough here, we are going to reduce this into the suspension of an empty triangle. Okay, so this is just a complex with 5 vertices. So a simplicial map from here to K will have its image contained in a simplicial cone, because the K is 8 conic. Okay, so these 5 vertices will be contained in simplicial cone. So this last map is certainly null homotopic, and therefore so is the original one. And this is the end of the proof. Okay, so this is the idea, a possible idea for the proof of this implication here. So let me just say that for the general case, so the general result is that for any D, not just 2 or 1, any D, there exists a degree of conicity, which implies deconnectivity. And the idea is to, well, generalize this proof is not, it is much more technical, and many other concepts are involved in the proof, but something like this is needed to consider certain triangulations of S3, S4, and so on. And remember that the application that we have in mind is with this and the original combinatorial, the probabilistic result, we're able to prove that any complex will be deconnected with the probability tending to 1 as the number of vertices tends to infinity. Okay, so this is the important application of this idea. Well, that's all I wanted to say. Thank you.
Great, thanks very much. Please thank the speaker. We have a minute and a half for questions.
Sorry. I try to go fast, but
it's okay. If nobody has questions, Martin, I'm sure, has one.
I can always ask a question. And say I found the proof lovely and super clever. So I'd love to hear about it for 1 more minute. But maybe the question is, where do you see the probability stuff that you mentioned in the beginning of the talk happening here?
Well, this is like a separate result. I mean, if you have this, the definition of R-conicity, I mean, every subcomplex of at most R vertices contained in a simplicial cone, you can give a lower bound using that you are in the medial regime. So all these probabilities P sub sigma are greater than or equal to some particular A, a positive A. You will be able to compute, is really an exercise to compute, to give a lower bound for the probability of a complex in n vertices being R conic. Okay, so I think you have to go, you say, okay, if it is not R conic, it means that there is a subcomplex which is small, which is not contained in the star of any vertex. But this is very unlikely if n is very big, because once you fix a subcomplex, how is it possible that it's not in the star of any of the vertices in the complement? if all these probabilities are bigger than A. So you compute what is the probability for every subcomplex of at most r vertices, and then you just consider, okay, what is the probability of an intersection, of a union? It's just perhaps it's a one-page proof, but it's something combinatorial. I remember it's something like that. You take complements all the time, and you always use that you have this lower bound A, and it's really something that you can, it's a bit long. I mean, there are like 4 steps, but if you decide what are these events that you want to, the probability that you want to compute, it's not hard at all.
I'm sorry, guys, we have to stop and introduce, sorry, Doreen, you want to say something?
Well, I just had a quick question, but if we're running out of time, then I will ask it at the end of the day.
Okay.
Yes, please. So, next speaker is Elizabeth Munch from Michigan State University in the States. Her talk is entitled The Interleaving Distance for Graphical Signatures. Please, Elizabeth, go ahead.
Let's find out if I can find my slides first. There we go. Can you all see that? Cool.